All right, we can go ahead and get started. Thanks so much for joining us today. We're really excited for all of you to be here and for today's session on our O'Donnell Awards and a recipient presentation from the award winner in Technology Innovation. Thanks for joining us. My name is Terrence Henry. I'm the Executive Director of TAMEST. That's the Academy of Medicine, Engineering, and Science of Texas. And before we begin our session, I'd like to tell you just a little bit about our organization. TAMEST supports collaboration to advance research, innovation, human talent development, and business in Texas. We are composed of more than 320 Texas-based members of the three national academies: the National Academy of Medicine, National Academy of Engineering, and National Academy of Sciences, as well as our state's 11 Nobel laureates. We're supported by the founders of our endowment, which allow us to operate and provide crucial financial support, as well as our 18 academic and medical research member institutions. We want to thank all of them today for their ongoing contributions to our research community and to the health and vitality of our state. Today's session is the final of 4 research presentation sessions highlighting this year's recipients of the Edith and Peter O'Donnell Awards. These awards play a vital role in recognizing and promoting rising star researchers in the state. The awards are named in honor of Edith and Peter O'Donnell, who have been steadfast supporters of TAMEST since its inception and incredible advocates for excellence in education and research. The awards are supported through the O'Donnell Endowment, and we'd like to thank and acknowledge the O'Donnell Endowment donors for their generous contributions to the awards program. The O'Donnell Awards Selection Committee is composed of 12 TAMEST members serving on 4 subcommittees, 1 for each award, plus the committee chair. And we'd like to recognize them and the committee chair, Kenneth Arnold, for their hard work evaluating the outstanding candidates over this past year. We'd also like to thank all of the Nobel laureate committee members who reviewed the finalists for the awards. So moving on to today's session, it'll feature a 20-minute presentation from the recipient of the Technology Innovation Award, Dr. Christian Davies. After Dr. Davies concludes his presentation, we'll have time for audience questions. And you'll be able to submit your question at any time during the session in the Q&A box, which you can find at the bottom of your window on Zoom. I'm now very happy to introduce the moderator for today's session, Anne Salamone. Anne Salamone is chairman of the board at Rochal Industries, LLC. She is a TAMEST member from the National Academy of Engineering and also served on the 2021 O'Donnell Awards Committee as the Technology Innovation Subcommittee chair. And she's serving as committee chair for the 2022 O'Donnell Awards. Anne Salamone, thank you so much for your service to TAMEST and for moderating today's session. We'll now turn it over to you.
Thank you, Terrence. It's my pleasure to introduce Dr. Christian Davies today. Dr. Davies is a principal science expert for nature-based solutions at Shell and an adjunct associate professor in the Department of Earth Sciences in the School of Natural Sciences at Rice University here in Texas. He is also adjunct assistant professor in the Department of Soil and Crop Sciences at Colorado State University. He received his PhD in ecology and microbial ecology in 2005, so he's a virtual baby, at the Institute of Ecology and Resource Management at the University of Edinburgh in the UK. He then pursued his postdoctoral training in the United States at the Odum School of Ecology at the University of Georgia under his advisor, Dr. Mark Bradford, before joining Shell Global Solutions as an environmental biotechnologist. A globally recognized expert in soil carbon bioscience, Dr. Davies is accountable for the development and delivery of R&D to support Shell's net carbon footprint ambition in an NCF through nature. His team undertakes projects aimed at protecting, transforming, and restoring natural ecosystems, such as forest, grasslands, and wetlands, while offering carbon neutral energy solutions to a growing number of customers. He was selected for the O'Donnell Award in Technology Innovation for his development of a broad suite of alternative carbon management technologies to reduce emissions for a lower carbon future. Dr. Davies' method of combining DNA sequencing techniques to analyze microbes in soil with net carbon flux. And novel soil carbon measurement technologies are shining light on the role that microbes play in carbon storage in soil, potentially leading to more storage capacity for carbon dioxide in soil. This discovery has led Dr. Davies and his team at Shell to approach the concept of carbon neutral fuel in a new way. The carbon neutral fuel accounts for the cost of storing extra carbon in nature and applies it as a credit to offset the use of conventional fossil fuels. The option to drive carbon neutrality is currently available to Shell's retail customers in both the UK as well as in the Netherlands. Please join me in welcoming Dr. Christian Davies.
Thank you, Anne.
You're welcome.
So I'm just going to share my screen and hopefully everybody can see that. Okay, so yeah, thank you. Good morning, afternoon, evening, everyone. Many thanks to TAMEST for inviting me to share a little bit more about our work on nature-based solutions. Again, it's a great honor to be the recipient of the 2021 O'Donnell Award in Technology Innovation. And today I will share a sneak peek into NBS and their carbon sequestration potentials, and then dig a little deeper, and that pun is definitely intended, into some more specific work that we've been doing to understand how carbon is sequestered in soil, and finally provide a kind of high-level overview of what NBS can mean for society as part of the energy transition. So when we think about carbon, we tend to really focus on what we can see. And this slide really demonstrates that seeing is not always believing. These are data from the 2014 IPCC report on global carbon stocks. And what I want you to notice is that, yes, there is a lot of carbon in the oceans, but this tends to change over much longer time periods. And plants and trees are really often what most of us think about when we think about carbon sinks in nature. But the reality is that there is much greater potential beneath the surface, below the plants, and beneath your feet. And in fact, there's actually more carbon in soil, as you can see from this figure. There's more carbon in the soil than both the atmosphere as CO2 and all the vegetation on the planet combined. But as we'll see later, soils are complicated. So if you think about NBS, we can broadly categorize them into these buckets. There are wetlands, which is predominantly carbon stored below ground, and that includes coastal restoration and protection of things like peatlands. A lot of projects currently in the voluntary carbon market are in the kind of forestry bucket. So a lot of projects that look to avoid deforestation, so preventing cutting down trees. But it also includes reforesting areas that were previously forest, in addition to afforestation, which is kind of planting trees where there were no trees before. Part of the forestry activities can also include things like improvement in forest management, and that can be changes in thinning cycles and rotations that lead to and translate to carbon accumulation in soil. But also management of nutrient inputs with the likes of fertilizer and lime to reduce GHG emissions. Agriculture and grasslands together cover a very large proportion of the land, provisioning very important ecosystem services for society in terms of food production. But there are also lots of opportunities for carbon sequestration in these managed ecosystems, from the integration of things like trees into croplands, so agroforestry, to again, manipulation, changes in the nutrient inputs that are associated with crop production systems that reduce GHG emissions, such as nitrous oxide. In grasslands, it can include restoration of both native grasslands and prairies to store soil carbon, but equally, we can change the way in which we manage animal grazing that can accelerate carbon storage in soil further. And the last one here is blue carbon, which relates to algae and plankton, but also more coastal marine ecosystems that we're probably more familiar with in Texas, with likes of seagrass meadows and other parts of the Gulf with mangrove and mangrove restoration. In both of those cases, the majority of carbon is stored below ground in the sediments. So how much carbon are we actually talking about when we think about nature-based solutions globally? This figure comes from a paper that was published in PNAS by Gresham et al. And in this study, the authors actually did quite an incredible job of trying to frame land use and available land for nature-based solutions, whilst accounting for multiple uses of land to avoid double counting of both areas where you could implement nature-based solutions, but also the carbon that can be stored, the carbon potential for each of these options. The scale at the top is in gigatons of CO2 per year and relates to stored carbon by 2030. And what you can really immediately see is that reforestation and avoided forest conversion of almost 15 gigatons of CO2 potential per year at a maximum. And it's more or less half of the total for all the NBS that they assessed that was possible in 2030. But planting trees can be expensive, and there are other considerations that we need to factor in, such as producing other ecosystem services from land that we use, that we rely on. The maximum values, which are the open white bars, they represent a cost to deploy those NBS activities that is in excess of $100 per ton of CO2. And so when we start to factor in cost, the agriculture and wetland options become more important, more significant. In total, if you look at this global potential for NBS activities, it would cover almost 50% of the terrestrial land surface area of the planet. So the potentials for storage are there, but it's going to need technology and innovation across many disciplines to try and help deliver that. So now I want to jump in to some of the details around one of my favorite topics, and that's soil and soil carbon. But first, I'm just going to kind of walk you through a little bit of a soil carbon 101. So not all soil carbon is created equal. We have different pools and forms of carbon that are going into and being stabilized in soil, from slow cycling soil organic matter that generally includes low molecular weight organic carbon substrate, so just think sugars in your head, that enter the soil as dissolved organic matter and associate with mineral surfaces, forming what we call mineral associated organic matter, or MAOM. It's kind of hard to pronounce. In addition, we also have particulate organic matter, and that's formed from slow decomposition of plant litter and roots, for example, things like cellulose and lignin. But particulate organic matter has limited protection from decomposition, unlike the mineral associated organic matter, and therefore tends to have a much shorter residence time in soil, but has no saturation limit. The third thing is that carbon utilization efficiency relates to the amount of carbon used for growth and enzyme production versus energy generation through things like respiration. So with low carbon utilization efficiency resulting in more carbon loss and less MAOM formation in this case. This figure was published by Rochal et al. In Global Change Biology, and it kind of eloquently outlines some of the potential mechanisms for carbon storage that are mediated by microbial processes in soil with regards to plant root soil microbe interactions. Essentially on the left, we have a system with plant roots, where you've got you've got carbon inputs to the soil of varying carbon utilization efficiency, so varying carbon quality is what we describe it as. Where at low carbon utilization efficiencies, the microbes in that soil rhizosphere actually mineralize a lot of the carbon to produce energy, which results in more CO2 loss, more respiration to the atmosphere, and less accumulation of mineral organic matter. Converse to that, where you've got high carbon utilization efficiency, the microbes are much more efficient in what they do with the energy that they're accessing for growth and biomass and enzyme production. That means more of that carbon is stabilized with mineral associations, so you get less CO2 respiration. Over on the right, where we don't have plant roots in the system, it's really driven by low microbial densities, and this is typically in bulk soil. So in this case, there's relatively little difference between these scenarios in terms of CO2 respiration, but what we do see are bigger carbon losses through leaching, which is largely driven by the surface area of the mineralogy. So next, I just want to get you back to kind of how we measure changes in carbon for nature-based solutions, be that in soil or biomass. And this is a key piece of nature-based solutions and our ability to resolve and quantify changes in carbon over time. So over here on the right, we have more up-to-date IPCC carbon numbers for the plants and soils and atmosphere. But what we also want to kind of point out here is that we've got the gross photosynthetic CO2 uptake by all the vegetation on the planet, and the gross respiration from soil plus plants. And what I really want to emphasize here is that these are pretty big numbers in terms of gross in and out, but the net land sink is only 4 petagrams of carbon per year. And what that means is we're trying to measure a relatively small increase in relatively large pools. And therefore, how we can measure carbon and changes over time spatially, we need to try and account for these complexities. I'm not going to go into the details of today in terms of the different approaches, other than to say that we can measure changes in the stock, we can measure changes in the flux in and out over time, or we can use mechanistic models to make these measurements for nature-based solutions. So into the field. And this is a site where we're testing different carbon measurement technology using combinations of flux towers, but also soil sampling methods to try and quantify those stocks. And here we have the towers that are measuring fluxes in and out in the middle of the land surface area over time. And then we've got this grid of 25 by 25 meter plots from which we took soil samples. This gives you the kind of sample flow and subsequent analysis. And what we really were looking to do was try and understand spatial drivers of carbon accumulation. So if you have in the back of your mind the Rochal figure in terms of the plant roots and bulk soil and the microbial interactions with that. So we're trying to understand what results in carbon accumulation and try and generate some data both on the carbon flux and the microbial role in where carbon was stored in this system. So we took 25 1 meter deep cores and then broke this down into segments, which you can see here by depth, and subsequently subsampled those segments for DNA extraction and RNA extraction and sequencing of both, in addition to sample processing for the different soil carbon pools. So for the DNA sequencing, we used this, it's not new, but it's newer technology in terms of Oxford Nanopore Technologies. MinIONs, not the yellow ones, the Minion. Our kids would love the Minions, but these are MinIONs, which is essentially putting sequencing capabilities into something the size of a USB stick that you can plug into your computer. So one of the benefits of this technology is that you can start to take it into the field. And if you're looking at things like RNA, you can start to do real-time RNA sequencing where RNA can degrade quite quickly and is not amenable to transportation and analysis back in the lab. The sequencing works by running DNA through small pores in the sequencer, and that's kind of what's being demonstrated on the right. It's not that clear. But essentially, once the pore is located, a motor protein binds to that pore and pulls DNA through the pore and measures the change in potential across the membrane, and then attributes that potential to each of the different DNA base pairs that are going through. The nanopore sequencing benefits over other technologies like Illumina in that it has much longer reads and improves the assemblies, especially over repetitive regions, and the longer reads can enable more accurate classifications by having fewer gaps to fill with shorter reads. So these are some of the data from the 1 meter core data plotted in 3D space with simple linear interpolation. And this is the mineral associated organic matter % carbon, where at the surface we see So this is looking at the top down, if this is the box, the cube, where we see some spatial heterogeneity. So over here in the top right, we have a higher % carbon than in other locations. But the other thing that you want to notice here is that it quickly drops off with depth. So below 30 centimeters, it really doesn't, we don't see spatial heterogeneity. When we look at the particulate organic matter carbon, we see a lot more spatial heterogeneity, both at the surface and with depth. But also you'll see it's a higher percentage carbon than the mineral associated organic matter. But here you'll notice on the right that the highest % carbon is actually at 60 centimeters depth on the left-hand side of this plot over here. I don't know if you can see the little laser pointer. So far, we've managed to process the DNA samples and do sequencing with the DNA. And this is just showing you the alpha biodiversity across the site and with depth again. And again, we can see lots more spatial heterogeneity, which may be associated with particulate organic matter carbon, specifically at depth here, and where we have lower biodiversity here and here, where we had a hotspot of particulate organic matter. We've done some initial correlations between malm carbon and the taxa that have been identified at a family level. And we do see some microbes that have been identified with not a great R value, but the top of the list is Verruca microbia, which is a root associated microbe. So our next step now, with all the data that we have, is trying to figure out, is the challenge of dealing with the quantity and volume and types of data that we have. So we're in the process of trying to apply machine learning across that full breadth of data to try and understand interactions between changes in the microbial community spatially with depth, but also metabolic pathways that are being up and down regulated from the RNA sequencing data. But essentially, I think I wasn't really expecting to see quite as much spatial heterogeneity. And I think we just flipped the light switch on in the TARDIS of the soil world. So from the technical potential of MBS, I want to kind of go back up to some of the what this means for society. So in Shell, we're working on many elements in the energy transition, which begin by avoiding the emissions of greenhouse gas into the atmosphere to begin with. So electric charge points, hydrogen, and renewables as the starting point. Then where we need additional sources of energy, we're going to look to reduce the emissions with use of things like biofuels, fuel efficiency, and LNG. And then lastly, where those emissions are harder to avoid and reduce, we provide customers with options to compensate for the emissions when they use Shell products through the use of nature-based solutions. So how do MBS work? So I've shared the different types of MBS and their potentials and some of what is measured, but essentially it involves the implementation of activities that result in carbon storage in biomass and or soil, where 1 ton of CO2 credit that comes from an MBS carbon project is equal to 1 ton of emissions that are compensated for. So from a carbon in a tree perspective, the average tree is about 0.9 tons of CO2 per cubic meter, and it can accumulate carbon over time from the point at which it was planted, anywhere from 15 to 100 years, depending on the tree, the species, the location, climate, and soil, etc. So when CO2 emissions are hard to abate, when a customer chooses a Shell product with an MBS CO2 credit compensating for the emission from the fuel use, there's a payment to help cover the cost associated with the development of the MBS solutions project and the Shell global portfolio. The projects and credits are independently verified to capture or reduce CO2 emissions in the various carbon markets such as Vera. But the key piece here is that 1 ton of CO2 credit represents the avoidance of 1 ton or removal of CO2. Such that when a customer completes their purchase, the credits then they need to compensate for their emissions are retired from the portfolio. When it comes to the types of fundamental criteria that we have for MBS projects in Shell, we need to really make sure that the credits are permanent. And under Verra, which is one of the voluntary carbon market registries, this typically means 100 years of permanence. The protocols also require that MBS project activity doesn't cause leakage, and that kind of goes back to the Grissel et al. Report where I mentioned that they'd accounted for dual uses of land to make sure that conversion into MBS doesn't impact land use somewhere else. But also, the credits need to be additional to what would have happened without the project. So projects are all assessed using approved accounting methodologies, and they've been developed by the carbon market registries like Verra. And it requires a baseline measurement and analysis to define what would have happened without an MBS project. The credits need to be real, also measurable, which means we need robust measurement, reporting, and verification processes that need to be in place to ensure both scientific robustness and credibility of the carbon stored. Credits are unique, so that goes back to this one-to-one accounting concept that was on the previous slides. But the independent verifiers, they're independent to the credit buyers, the project developers, and the registries. And they are essentially there to check projects for performance, so making sure that they're storing as much carbon as we think they are, the accounting processes, and also physically go and visit project locations to make sure that the activities that are in the documentation are actually being implemented in the project. And lastly, the credits are only ever issued after the emission reduction or removal has been verified. So technology, I think, has a really big role to play across this space. This final slide just gives you the global reach that MBS has in the current Shell portfolio across lots of different project types. So you'll see it covers conservation of existing forest, reforestation, in addition to afforestation. And last but not least, I just want to thank the people that were instrumental in making the things that I've talked about today possible. Thank you.
Thank you, Christian. It's a very interesting presentation, and certainly very different from others that we have heard at TAMEST and perhaps at the National Academy of Engineering as well. So now we'll begin the question and answer component of this meeting. As soon as I can open up the Q&A box. In the meantime, I'm going to ask you one of my questions while I'm figuring out how to get to the Q&A box. You bring up an interesting application of monitoring microbes. Do you foresee, as an outshoot of what you have developed at Shell and others have developed, a new industry of creating microbes that are specifically going to be utilized as fertilizer, if you will, for carbon dioxide capture in soil?
I think there's definitely going to be applications in that space. I mean, there are a number of companies that are starting to do microbe inoculations for soil. So going beyond things like fertilizers to enhance yields or productivity. But I think there's probably definitely a lot of opportunity in that space, either through inoculation with specific groups of microbes that might facilitate additional carbon uptake or have specific plant root associations, but also a better understanding of actually what the microbes are doing in soils also would give us opportunities to manipulate the system through other means, through land management or activities. So I think we have always struggled with to unlock what's happening because as you know, Anne, it's probably less than 1% of the microbes that are in there that have actually been isolated and cultured, right? So we are dealing with a black box, and we're really only I think the molecular tools are really now only cost effective, at a cost price point to do the analysis that we'll start to use them in more of these types of applied systems. Because as you know, the cost of sequencing has come down quite a lot since the Human Genome Project.
It has, and much easier. Thank you. So we have a question from Richard Dixon. He says, we often hear about the beef cattle industry as a major source of greenhouse gas emissions. What opportunities are there for reducing this footprint?
Yeah, I mean, so there's a lot of work that's been ongoing, that's being published, and a lot of debate with the likes of Richard Teague at Texas A&M that are looking at, I guess, rotational adaptive multi-paddock grazing approaches to managing grazing cattle. And that has two effects. One, it has an implication in terms of the enteric emissions of methane. When you change that forage quality, that might actually reduce emissions when you switch to that type of activity. But also we're seeing increases in soil carbon that, I think somewhat relates to the microbial processes that are happening when you implement that type of grazing. So I think there's definitely an opportunity for the beef cattle industry to actually be the opposite, be a carbon sink.
Okay, so I think you've answered this question, but I'm going to ask it also. So Oliver Mullins has asked, a very nice presentation, thank you. There is significant deforestation associated with cattle ranches. Are there efforts to improve the CO2 footprint in the food industry?
So we are seeing that in terms of, the likes of McDonald's have kind of put out their sustainability, I guess, not benchmarks, but certainly targets in terms of what they want to do with sustainable beef production systems, and that avoiding deforestation piece would be a key element of that. I think that then goes hand in hand with what I mentioned earlier in terms of changes in the way we manage animals, because I know in Brazil, there's a lot of poorly managed grazing land that just results in pasture degradation to the point where it is just a termite field, basically. So when you manage land to manage the system, then you start to decrease the total areas that you may need for those production systems, which also in turn could reduce the indirect effects of things like deforestation.
Thank you. Okay, so Lisa Biswal has said, thank you for the interesting presentation. With carbon dioxide sequestration being considered in depleted reservoirs, how do we compare the capture potential soils versus rocks? And hold on a minute, I thought there was, oh, wow, my screen is going like crazy. Okay.
Are you asking if the CCS, how does CCS compare, I guess?
Yeah, so how do you compare capture potential soils versus rocks? Let's do that.
I think some of it goes to the global scale, right? So there's 3.5 billion hectares of pasture and grassland on the planet globally. So I think, you might have a lower concentration overall, but the sheer number of hectares makes up for that by orders of magnitude. I mean, I think the Grissom et al. Data is definitely pretty extreme in terms of, the paper said they're going to switch everything on tomorrow globally. So tomorrow, 50% of the Earth's land surface is NBS. That's not going to happen, right? So you'll see some of the updates that we've done to the shell sky scenarios that do account for more realistic temporal dynamics in terms of the rate at which you could implement NBS. And certainly the total global potentials come down quite a lot, but it's still in, the 10 or more gigatons of CO2 per year range at its peak.
Thank you. Okay, Kishore Mohante has asked, you showed a slide about Shell's electrification and hydrogen, et cetera. Can you please show that slide and say a little bit about different approaches that Shell is taking?
So the one where we've got the avoid and reduce, right? So we're investing a lot in the infrastructure to distribute hydrogen, right, to customers, in addition to technologies that will produce hydrogen at scale. Places like Germany are quite far advanced in that space. On the electrification side, we obviously are investing in both the supply, so renewable solar and wind, in addition to the kind of then distribution customer touch points with electric vehicle charge points, but also provisioning electricity to customers in their homes. So those things are accelerating. They're going to grow. They're going to be a big part of the future in terms of energy.
Yeah, yes, I'm sorry, but I have to ask, how many of your wind turbines and solar panels were frozen 2 weeks ago in Texas?
Personally, I don't know the answer to that question, but as you know, all of those things can be in various climates still operating, right, with similar or more extreme conditions. So it's just a question of how often you think that's going to happen and how much it's worth to pay to prevent that, right?
Yes, yes, yes. Okay. So Kishore Mehta asked, am I correct in thinking that oil and gas have concentrated carbon? Your suggestion is to store carbon in soil and low concentrations. Comments, please.
Yeah, I mean, it's definitely, you get if you tap into an oil reservoir, then the carbon obviously is coming out quicker than what you can put it back in the ground. But I think it's going to be a combination of CCS, alternative sources of energy, and nature-based solutions. So the updated sky scenarios do demonstrate that we can achieve 1.5 degrees C and limit warming to 1.5 degrees C, but it's going to require all of the above and rapid rates of transition. So yeah, it's not going to put the whole genie back in the bottle, as it were, but it's going to do a lot. It is a significant sink that is a material contribution to 1.5 degrees C future.
So this next question from Russ Conser is, what's the biggest limiting factor on how fast we can scale up NBS to be a material factor in the planetary climate equation, which leads right into your comments?
Yeah, people.
Mm-hmm.
People is the biggest limiting factor, both on the consumer demand side, right, of the things that we choose to pay more for, right? So I pay more to have 100% renewable electricity, but that's my personal choice, right? Not everybody has the resources to do that, or even the will to do that, want to do that. Mm-hmm. But ultimately, on the land use side, it's trying to incentivize, not just through nature-based solutions projects with financial payments for carbon storage, but governments have a pretty significant role to play as well, right? With the things they signed up to at the Paris Climate Accord, and actually making real progress on that, right? So, and nature will play a part in that as well. It's not easier, but for sure, governments they have natural resources that they can use to contribute to the NDCs that they've set. But it's the people piece that's going to be the hardest bit, getting people to change at scale.
I think it's difficult to understand that people are part of nature, I think, and that we have to.
Yeah, we can certainly solve a lot of the technical challenges with it. Mm-hmm. But at the end of the day, it needs somebody that is responsible for managing an area of land to make that decision to say, yeah, I'm going to do that. And it's not just do that for the next 10 years, right? So 100 years of permanence with Vera, mm-hmm. You're signing up to 100 years of keeping it that way, right?
Yeah, yeah. So we have time for one more question, and this is from Oliver Mullins. And he says, for much of the Earth's history, microbial mats dominated life. Are there efforts to consider ways to reinvigorate microbial mats for carbon dioxide storage?
I don't know is my answer, honestly. I would assume that some people are looking into that, but personally, I don't know, would be my honest answer.
Okay, Terrence, you want me to wrap it up now? Is that correct?
I think we can actually fit in that last question. We have a couple minutes left.
Okay. So the question is there another question on the screen? The first question is still the one?
I believe it's from Bob Metcalf.
Okay, never mind.
Yeah.
Bob Metcalf. Geothermal energy. Might your measurements of microbes at 1 meter help locate concentrations of carbonless geothermal heat 1 to 10 kilometers down? Thank you for that question, Bob.
Yeah, I mean, so there are examples of using surface microbiology to infer processes that's happening in terms of reservoirs and identifying an oil and gas reservoirs. So we do know those techniques have been applied to exploration, but also leakage and leak detection as well, right? So yeah, I think it's a question of just understanding what the drivers are, the driving variables that you're looking for. But the microbes, you got to remember the microbial processes and changes in the community are going to be reflecting relatively short time scales because they're pretty dynamic in terms of the communities, and that composition will change over time. It's one of the reasons we need to go back to the site that we sampled to resample to look at how that community has changed. And but yeah, I think there is probably potential.
I was going to ask something similar to rare earths, but we don't to finding them, but we don't. I'll talk to you about that later. Using the microbial presence for those sorts of explorations as well. So thank you, Dr. Davies, and our audience today for the informative presentation and questions. I'd like to congratulate you again on receiving the 2021 O'Donnell Award in Technology Innovation. And I'll now turn it back over to Terrence Henry to conclude today's session.
Thank you, Anne. Thank you, Terrence.
Welcome. Thank you.
All right. So thanks again, Anne Salamone, for hosting today's session and moderating. And Christian Davies, thank you for sharing your fascinating research with us. And congratulations again on your award. We're going to have video and slides of today's session posted on our website. And you'll also receive links to those in a follow-up email tomorrow. And we'll also have a survey for you to submit your feedback on today's session. We have nominations now open for the 2022 O'Donnell Awards, and we have information about the awards, including the nomination guides, on our website. That's at tamest.org. We'll also share a link to that website information in that follow-up email tomorrow. Would really encourage you to take a look and help find the next generation of rising star researchers in Texas. We're also going to have an informational session in a couple weeks on Thursday, March 25th, to go over the awards selection process and answer questions from attendees about what's involved with nominating and selecting the O'Donnell Awards. So you'll also get a link to register for that tomorrow, and we'd encourage you to join us and bring your questions to the session. The nominations will close for the 2022 O'Donnell Awards on April 30th. We also have an event a bit far off into the future, but are looking forward to it more each day. Our January 2022 annual conference, which will take place in San Antonio, and it's going to focus on community health and well-being. We're going to explore how Texas can build the vibrant, healthy communities of tomorrow and address topics like healthcare, housing, and infectious disease. So once again, we'd like to thank Dr. Davies for your work and sharing it with us, and congratulations again on your award. And thanks to each of you for joining us. Hope you'll stay safe. That concludes our session for today, and hope to see you again soon. Thank you.